So we'll start by actually explaining what is a nucleophile and what is an electrophile. So a nucleophile is either a negatively charged ion, so for example, something like Cl minus, which has a region of high electron density, or I guess the ion itself is the entire ion is highly electron dense due to the excess of the electrons. So that's what's giving it the negative charge. Or something like, for example, you could have a ketone like this, like propanone, and the nucleophilic part of this is going to be at the oxygen atom because oxygen is more electronegative and it's going to pull these electrons from this double bond closer towards the oxygen atom itself. So that is going to attract the nucleus of another atom, which is positively charged. And that brings me to the next part. So what is the electrophile? So the electrophile is the opposite. It's going to have low electron density, giving it a partial or complete positive charge at the electrophilic atom. So that's something like, for example, hydrogen is electrophilic because it's got this positive charge. So it's just the proton, and it would like an electron to balance it out, basically. So, or you could also have a polar bond again, and we can use this example the second time. So propanone, it's going to be electrophilic at the carbon because this oxygen is pulling both of the bonded electrons closer to it, and then it's further away from this carbon, which gives it a partial positive charge. So to distinguish between electrophiles and nucleophiles, you're going to want to look at two main things, and we've already touched on it a little bit. So that's going to be the charge and the electronegativity or polarity of the compounds. So, for example, like I'd already touched on, if you've got a negatively charged ion, like a chloride ion, that's going to be nucleophilic because it is electron dense. So it wants to give up that electron. And then you've got something like hydrogen, which we've also already touched on. This really wants an electron, so that's going to be electrophilic. The second thing, which we also have already kind of touched on a little bit, is the electronegativity and polarity of any kind of species. And this can kind of be applied to any sort of reaction that you're looking at, depending on the compound. So if you've got something like chlorobutane or 1-chlorobutane, this is going to be, again, it's going to be nucleophilic at the chloride, and it's going to be here. It's going to be electrophilic at the carbon, because this, even though it's given up its electron, or it hasn't given it up, it's covalent, it's still hugging it closer than the carbon is. So now I've made two examples, and in the first example, which is this one here, which one would you think is the nucleophile and which is the electrophile? So this one's a pretty easy one, but because of this positive charge on the ammonium ion, this is going to be the electrophile, and bromine, because it's negatively charged, is going to be the nucleophile. So these are the products, which is ammonia and hydrogen bromide. So the second example gets a bit more tricky. This is why it's important to actually have a reaction to put everything into context, instead of just identifying the nucleophile and electrophile. So in this reaction, which one would you think is the nucleophile and which would be the electrophile? So this is an acid-catalyzed esterification reaction, which you might have seen before in high school or whatever, but the nucleophile in this case is going to be the alcohol, and it's going, and specifically the oxygen, which has a lone pair in this case, and the electrophile is going to be this carbon in the carboxylic acid. You might be thinking, well, what about the polarity of each molecule. So this bond, you'd be correct in saying that this bond here is polar, and it's polar with a more negative oxygen here. So this would be the delta minus, and this would be the delta positive. But the reason that the ethanol acts as the nucleophile is because here, this bond that I've circled is much more positive because of the double bond between oxygen, which is a delta negative, and then another single bond between the alcohol, the oxygen and the alcohol, which is also delta negative. So this is going to be much more positive with respect to the carbon. And so essentially what happens is the lone pair that I said is going to attack this carbon, and it's going to kick off this hydroxyl group, which is then going to react with this hydrogen, and form water, and it's catalyzed by an acid, which can be any acid, but in solution it's going to be hydronium. And it's going to create this compound here, which is ethyl acetate. And I'm sorry that it got a bit messy, but it's just hard for me to rub everything out without rubbing out the entire reaction. So the last part of this lecture is going to be how substitution is going to affect the electrophilicity of a carbon. So I'm going to use alkyl halides as an example to illustrate this. And if we've got something like this, which is 1-chloropropane, then it's going to be electrophilic at this carbon, which is the first position carbon, which we've already covered, and you should be able to do that by now. But if we've got something like 2-chloropropane, then it's also going to be electrophilic at the second position carbon, so the second position carbon. And we could have something like this, which is 2-chloromethylpropane. And in this case, it's also going to be electrophilic at the second position carbon. But which one of these is going to be the most electrophilic? So when you've got a highly substituted carbon atom, which is bound to whatever the group is, which in this case it's going to be the chlorine group, then the more substituted that this carbon atom is that is bound to the chlorine is going to determine how electrophilic it is. So when you've only got one other carbon atom bound to the electrophilic carbon, it's going to have less of an opportunity to balance out the charge. Whereas if you've got two carbons bound to it, these two carbons are going to only slightly balance the charge. So they're going to take some of the positive charge that is going to be felt by this carbon. They're going to take some of that, only a little bit though. But if you've got a tertiary alkyl halide like this charge on this carbon, the positive charge is going to be shared between three carbons. Each is going to take a little bit, and it's going to make this less positive than the primary alkyl halide. And the secondary alkyl halide is going to be it's going to be more positive than the tertiary alkyl halide, but it's going to be less positive than the primary alkyl halide. And that's because, like I'm saying, it can share some of this positive charge between the bonded carbons. So in this example, even though you've got the same halogen bound to a carbon atom, not each of them is going to have the same electrophilicity because of the substitution, and that allows the carbon to share its partially positive charge between the surrounding carbon substituents. Thank you for watching this lecture, and the next one is going to be on nucleophilic addition.